All right, so this video is about inverse relations. Now, inverse relations are something that you should have studied in grade 11. Just like a few of the other topics we've covered so far, you're expected to be coming into this course with some background knowledge. At the same point, we are going to spend some time going over it just to make sure everyone is on the same page here. So an inverse relation is created by interchanging, which means switching your x and y variables. So that means if you have a point that's on your initial function and your point is 1, 3, then on its inverse, that point would become 3, 1, where we have interchanged, where x has become y has become x. The inverse relation applies the opposite operations. Okay, so let's say our function is f at x equals x squared. Then the opposite operations will be applied in reverse order. So rather, let's make f at x equals x squared plus 1. Then we're going to be working in reverse order to break that apart and and come up with our inverse function. Now we will actually see that in practice down below, so I'm not going to break this one down. The inverse of a function is a relation, but it's not necessarily a function. Okay, you might have, even though f at x is a function, its inverse may not be a function. The inverse is a reflection over the line y equals x of the original relation. Now we've talked already in here about reflections. We've talked about reflecting a function over the x-axis or over the y-axis. We've talked about symmetry, about even symmetry, which is related to a reflection over the y-axis. We've talked about odd symmetry, which is related to a reflection over the origin. But here we're going to be reflecting over the line y equals x, right? And that is our standard base linear function. Now, if a relation is a function, then we write it out in function notation. Then we're allowed to write it out in function notation, and we can write it out as f at x. If an inverse is a function, then we can write it out as f negative 1 of x. Now, both of these together mean that f negative 1 of x is an inverse of f at x. Okay, so it brings our function notation to one more level. Now, first off, let's try and find the inverse of this function here. This function, we're not given a particular equation. We're given a set of ordered pairs, right? So the inverse, and we can here we can use the inverse function notation here. The inverse function can be given by, again, interchanging our x and y values, our x and y coordinates. So if we have the point, and let's open our set with a squiggly bracket again, and then a dot, dot, dot. If we have the point 1, 2 on our base, or on our original function, then on its inverse, we'll have the point 2, 1. If we have the point 3, 4 on the original function, the point 4, 3 will be on its inverse. And if the point 5, 6 is on the original function, then the point 6, 5 will be on the inverse. Now, if we're working with this function here, let's try and evaluate the inverse function at 4, right? So this is, again, we're using our function notation. The inverse function at 4. Okay, so that means x equals 4 for our inverse function. That means right here I can see a point where x equals 4. The y coordinate would be 3. That is the value of our inverse function at x equals 4. Good. Now let's try and evaluate f at f negative 1 at 2. Okay, so we're evaluating the inverse function at 2. And evaluating the inverse function at 2 brings us the value 1, because that's our y coordinate there. So that means f at 1 is what we're looking for. Now, f at 1, we still need to go back on where we were working, our original function in here. F at 1, I can see that equals 2. Okay, now let's see if there's a connection there, see if there's a pattern we can come up with. Let's try again. Here we'll try f at 5. We'll evaluate that first. Remember, here we need to work on the inside and then go outside with our function notation. So f at 5, we're looking for f negative 1, f at 5. Well, f at 5 equals 6. And then f at negative 1 of 6, So I can go over to here, equals 5. Okay, so now this is a bit of a pattern, and I will I'll spoil it for you. It absolutely is a pattern. So we see here that f of negative 1 of a value brings us that same value. And we see that f at negative 1 of f of a value brings us back to that value. So what we're really learning here is that f and f at negative 1 cancel each other out, right? Which kind of makes sense if we think about it. A function and all of its opposite operations, right? A function and all of the opposite operations of that function should cancel each other out because of the way an inverse function is built. So that means f at negative 1 of x equals x. And that means f negative 1 of f at x equals x. Either way, either time, f and f negative 1 will cancel one another out. Okay, now let's get into sketching a function here. We're going to start off and we're working with a very simple linear function. Now, if we're sketching the inverse, we can do so using a number of strategies here. The strategy I'm going to give us, actually, we're not going to work with these points exactly. You know what? I will leave them there, though. What we're going to do is, if we remember up top here, we mentioned that the inverse is a reflection over the line y equals x. So here we're going to take that property into effect and we'll try and use it to our advantage. So that means we'll start off and we can sketch the line y equals x. There we are. It's a linear function. Its slope is 1. Y equals x. That's not a very nice y, is it? Good. We're struggling here, and that's okay. Now, what we're looking for is a reflection over this line. So that means if I have a point that crosses the line, and this one over here does, if I have a point that crosses the line, y equals x, a reflection over this line, that point will stay in the same spot. So that means our inverse will have a value there as well. We'll have a point there as well. Now, otherwise, what we're doing is we're reflecting over this axis. So here I can look and I can bring this over, or reflecting over the line y equals x. Again, we're going to bring this over. We're going the same distance away from the line, just straight across on the other side. Now, if our function crosses the line, that means our inverse function must also cross this line y equals x. And we're building our inverse just through reflecting it over our linear function y equals x, over our base linear function y equals x. And so our final inverse function looks something like this. Okay, whoops. And we can label this f negative 1 of x. We could see here that time really actually we shouldn't quite label it that yet, and that's okay. So we'll leave that. Now, we would like to state the domain and range of f at x. F at x, that's the red one. That's the one we began with. So our domain and range of f at x, the domain, x is an element of the reals. Our range as well, y is an element of the reals. Good. Now we want to go in and sketch state the domain and range, really, and range of the inverse. So again, in this case, we can pause. You can pause the video here if you would like. Practice it. Try it out on your own. But I'm going to write the answers right here. Our domain, again, x is an element of the reals, and y, whoops, and our range is y is an element of the reals. Now, is our inverse here also a function? We know our first one was a function. It was given in function notation, and it would have passed the vertical line test. So we can double check here and see if our inverse will pass the vertical line test. Let's give ourselves a vertical line. Luckily, we're masters of the vertical line test at this point. We're masters of seeing if something is a function. And we compare, we're just looking at the inverse here, just looking at the green function. And as we go along, we can see that it does pass our vertical line test because it only crosses this vertical line once at a time. So yes, our inverse is also a function. So if our inverse is also a function, that's what allows us to label our inverse with the notation f negative 1 of x. Okay, now, and I'm sorry for zooming all over the place. I'll try and figure out how to avoid that in future videos. If our equation, if the equation of our original function is f at x equals 2x minus 1, then we want to here algebraically determine the equation of its inverse. If we wanted to, if this did not specify algebraically, we could just analyze this line and come up with its equation, but we're not going to do that. We're going to algebraically find it. So again, here we're going to go back up to the basic properties we had, and we'll note here the inverse relation applies the opposite operations in reverse order. It's the undoing of a function. Okay, so we're going to take advantage of that, and we'll try and algebraically come up with the equation of the inverse. Now, an inverse function, if we remember from the start, an inverse function interchanges the x coordinates with the y coordinates. So here, what we want to do in every single time, folks, if you are looking to get full marks, algebraically determining the inverse of a function, then you must communicate what you are doing. So you must say, I'm going to put quotes around it. You don't need to put quotes around it, but I'm going to have those there to emphasize that you must write this in. This is not just extra communication. This is necessary communication. So we're going to switch, or you could write interchange x and y. Okay, so now that we've written that out, it mathematically will make sense to write this as x equals 2y minus 1. If we do not communicate this, if this communication is missing, then mathematically it makes no sense how we go from the given equation to this equation down here. So you would not gain full marks for that. Now, what we want to do with our inverse function is we want to break apart the original function and apply all of these operations in the inverse order. And that means basically what we are looking to do is isolate for y, right? So here what I need to do is I add 1 to both sides. So that's x plus 1 equals 2y. And that means y equals x plus 1 over 2. So this is the equation of our inverse. Because it passes the vertical line test, we can write this as f negative 1 of x equals x plus 1 over 2. Okay, moving on to example 3. Here, we're going to work with a quadratic. So it gets a little bit more complicated, just a little bit, and we'll see the implications of this. So now I know on your page you don't have these lines filling it out, and that's okay. I do want you to consider this as the full function. So consider these this parabola is sketched in, but I did want to emphasize these points. We're going to use these points to graph the inverse, so we really want to focus on those. Okay, so we're focusing on these. We have here 4 points I've labeled. The others we can find the coordinates. Now, we're looking to use, so let's say we have the point 3, 8 on our original function. That means, from the definition of an inverse, that means that the point 8, 3, with those coordinates switched, 1, 2, 3, 4, 5, 6, 7, 8, just counting them out, 8, 3 is going to be on our inverse function. Okay, now that also means the point 8, negative 3 will be on our inverse function. I'm hoping you can see right away, 8, negative 3, I'm hoping you can see right away whether or not our inverse will be a function or just a relation. And we can take the rest of the points as well and plot their inverse points. If you'd like, what I would encourage you to do here is pause the video, try it out, try sketching your inverse, and then unpausing and see if yours looks like mine. I'm going to plot it right here. I'm going to use the point, 3, 2. Sorry, I'm going to plot it while making mistakes. 3, 2, and 3, negative 2. And then I'm going to plot the point here, negative 1, 0. And there we are. So our inverse function looks like this. And we notice here, if we were to, just checking it, if we were to sketch in our linear function, our base linear function, y equals x, I can see that it looks like the green function is a reflection over the line y equals x of the red function, and that's a good thing, right? But we were not using this reflection necessarily to come up with this particular sketch. Here we were using the individual points. Now, stating the domain and range for both. Oops, I left these up, and that's okay. The domain and the range for both. What we need to notice here, so our domain, I hope you can confirm here, pause and confirm these are our domains and ranges that we're working with here. Since we came up with this inverse function by interchanging the x and y coordinates, again, since we came up with our inverse function here by interchanging our x and y coordinates, then it makes sense that what was our domain, where there was no limit on it, is an element of the reals, becomes the range of our inverse function. Okay, now what was the range of our original function? Y is an element of the reals such that y is greater than or equal to -1. That becomes the domain of our inverse function. And again, that kind of makes sense because we're interchanging all of the x and y variables, and we remember our domain is all of the possible x values of a function, the range is all of the possible y values of a function or relation. Then it makes sense that the domain and range will switch as we go from a function to its inverse. Now, determining the equation of its inverse, what I would like you to do here, let me see, sorry, bear with me here. We are going to algebraically determine it, but we're also going to look and sort of try and predict here. So here, if we're working with this green function, we might be able to recognize what kind of a shape this is. It's very, very similar to one of the base functions that we've studied so far. Now, it's similar, but it's almost as if that base function is appearing more than once. So pause the video here if you would like. Try and predict what our base function will be of the inverse here. What we need to recognize as well is that we're coming up with this. It's going to be the inverse of a quadratic. Well, what's the opposite of squaring something? The opposite of squaring something is square rooting something. So I think it makes sense, since we come up with our inverse function by performing the opposite operations, it makes sense that our base function of our original, if it's x squared, then our base function of our inverse function will be the square root of x. And that lines up with the shape that we're working with down here. Now the shape, though, has two arms. We know a radical function only has one arm, right? An arm being this part or an arm being that part. So we're going to need to manipulate this a little bit more. Okay, so what we're working with, let's try and algebraically find it. So we're working with f at x equals x squared minus 1, and we want to interchange or switch x and y, right? Again, we must write this in. Once we've done that, then we're working with x equals y squared minus 1. Y squared minus 1. Okay, well, now I need to isolate for my y, so that means x plus 1 equals y squared. In order to isolate or to further our progress here, we must square root both sides. If we are square rooting both sides, that means we must take plus or minus the square root in order to consider all of the solutions. So that means we must be working with here plus or minus the square root of x plus 1 equals y. And here you see from this plus or minus, right in here, from this plus or minus, you see that our outputs, the number of outputs for each input will be 2. For every single input that goes into this inverse, we're going to have 2 outputs, and that might predict whether we're working with a function or not. Okay, if we're double checking what we're working with here in terms of both arms of this inverse function, then we have here a radical function that is being translated 1 unit to the left, and that's the first arm. And the second arm is a radical function that's being translated 1 unit to the left and reflected over the x-axis. Now, again, we can see two arms in our original function here in red, so we must have two arms in our inverse function in green here, unless we're told to manipulate the problem in another way, which you'll see. So is this inverse a function? Pause the video, guess, try and figure out. Absolutely not. The inverse is not a function. We can tell that right away from the two outputs for each input down here. So algebraically, we can tell that. We can tell that by having two outputs here that share the same x coordinate. And we could double check just on our own, just by performing a vertical line test. You know what? You have done that plenty in this course. I'm not going to go over that again. If the inverse is not a function, and that's a check, it is not a function, we're asked to restrict the domain of f at x, so of the original, of the red function. We're asked to restrict the domain of f at x so that its inverse is a function. Okay, so we're looking here, and we must restrict the domain. That means we must change the red function in a way that its new inverse would pass the vertical line test. Okay, so what that is going to mean is we're going to have to take away one of the arms, whether it's the left arm or the right arm. We must take away one of the arms, otherwise our inverse will not be a function. Okay, so if we're taking away one of the arms, that means what we need to do, and it tells us we're restricting the domain, so that means that our new f at x equals x squared minus 1, so I'm just getting that right from the top here, equals x squared minus 1, and now we restrict the domain, and we say, okay, but x must be greater than or equal to 0. All right, so that's one possible solution. The other possible solution is to restrict the domain in the other way and include only the other arm, in which case we'd be working with f at x equals x squared minus 1, where x must be less than or equal to 0. Okay, either way, we're left with only one arm of the original function. If there's only one arm of the original function, then its inverse function will also have only one arm. Now, example 4, we are just going to power right through this, folks. Most of the examples in this lesson we are going over. We are going over here in the video. So we're going to work here. We're given this quadratic function. It's being transformed, and we want to find the ordered pair 3 and f at negative 3. Okay, so if we substitute in negative 3, then we're working with f at negative 3 equals 2 times negative 3 plus 3 squared minus 4. Okay, so that is 2 times 0 squared minus 4, and that leaves us just with negative 4. Okay, so what's significant about this point? Well, the point, negative 3, negative 4, is our vertex. Okay? You should be relatively familiar with that from grades 10 and 11. If not, you can recognize that what is now our transformed form is also with a quadratic is vertex form. Okay, where negative 3, so our p-value minus 4, p-value, comma, q-value, that's our vertex. Now, what's the vertex of the inverse? We would take our these coordinates and we would interchange them. So the vertex of the inverse is simply negative 4, negative 3. Now, determining the equation of the inverse function, what I would like you to do is try that one out on your own, okay? Or else we will go over that as well in class. Okay, so try that out, restricting the domain as well. I want you to try that out. You're following the same pattern that we followed, the same logic that we followed in example 3 up here when we restricted the domain. You should be able to handle something like that, right now. And pushing forward into example 5. So we just need to be careful. Okay, sorry. With example 5, we need to be careful. We're going to start off and we'll try and find the inverse of f at x graphically. If we're finding it graphically, that means we must graph f at x and then sketch in the line y equals x. Try and reflect it. So try that out on your own right here if you would like. F at x equals negative, so it's reflected in the in the x-axis. Negative, our radical function, plus 1, so it's translated 1 unit to the left, we should be working with something like this. Okay, it's just a rough sketch. Now, what we want to do is we want to plot or sketch our linear function y equals x, and we can label that as well y equals x. And what we're going to do is we're going to try and sketch graphically how this new function would look like if it were reflected over this line. So for each point, we're going to put, and I know we don't know particular points here, although we could do so. We could find them out, but we're going to try and predict what we're looking like. It's something like this, right? That is a reflection. This shows a reflection over this y equals x line. So if we're looking right here, then this looks like one arm of a parabola. Right now I could draw in a second arm here, and this second arm would still allow my inverse to pass the vertical line test. The problem is this second arm makes my inverse no longer look like the inverse of the original function. So we need to be careful. We must stay consistent with our original function. So we must take that away. I'll label them here, f at x. And the inverse, it's also a function. You could double check that if you wanted to, f negative 1 of x. We can see here that we must only work with one arm. Now, fantastic. Let's go into algebraically finding that. You should be able to do this on your own, but we want to be careful, right? We need to stay consistent with the function that we began with. So, algebraically, first we start off and we do this every time we write out switch x and y. Okay, so we're going to do that. That leaves us with x equals negative the square root of, y plus 1. And then I'm isolating for y. So I multiply both sides by negative 1. That is negative x times the square root of y plus 1. Now, what's the opposite operation of square rooting something? Squaring something. So I can square both sides. That leaves me with x squared, right? A positive x squared. And maybe I'm doing a little bit too much in one step. So negative x all squared times y plus 1. Okay, that leaves me with, now I can simplify this, negative x squared. If I square something, I'd lose the negative. So x squared minus 1 equals y. This is my inverse. But if I were to sketch this inverse, again, if I were to sketch this inverse, then I would be left with two arms. We cannot work with two arms because two arms does not fit in the context of this problem. So we must limit the domain here and state that x must be less than or equal to 0. Right? We can see that right here. We're using the red. The red is the inverse here. We must then limit it in the direction of the red. We cannot say, we don't have the option, the flexibility of choosing either red or gray. Okay, so this should allow you to handle all of the problems in lesson 1.5.